all together.
Okay.
Yeah.
Okay.
So welcome, John Yu. Would you like to introduce your talk? Yeah.
Sure. Okay. Okay. Good morning, everybody. My name is John Yu, and now I'm working in the Petroleum Recovery Research Center at New Mexico Tech. Today, I'm very pleased to share the work done by our research group. The title of today's presentation is Design and Optimization of CO2 WAG Projects Using an Artificial Intelligence-Assisted Computational Framework. Since this work is related with the Southwest Partnership Project, so firstly, I would like to give you a brief introduction to the SWP project. SWP is one of 7 partnerships funded by US DOE to study how to safely and permanently store CO2 underground. Each of these 7 partnerships is planned to inject and store over 1 million tons of supergenic CO2 underground. So as you can see in this figure, the SWP covers 8 states in the Southwest American. So now SWP is undergoing its phase 3 study at Farnsworth Unit Field, FWU. FWU is an active CO2 EOR project at Anadarko Basin, Texas. So the role of SWP is to characterize the field and also monitoring for the evidence of any change of the background level underground, and also simulate this CO2 EOR project. At FWU, we already collect a tremendous amount of information. We use this amount of information to build a detailed model to simulate the oil production, CO2 storage, and the CO2 movement through the reservoir. We also installed several tests at FWU to validate this model and also monitoring the effectiveness of the CO2 injection and the storage operation. It has been proved that at FWU, the injection of CO2 is a good way to produce more oil from this mature field and also store some of the CO2 underground at the same time. So here are some of the facts about the CO2 injection. As February 2019, there was about 1.36 million tons of CO2 has been purchased. And out of them, there was about 1.26 million tons of this CO2 has been stored underground. That takes about 93 of the total purchased CO2. So these slides give you some of the basic concepts about the water alternating gas, or WAG technique. So the WAG is one of enhanced oil recovery techniques. It helps to produce more oil. It helps to produce the residual oil left in the reservoirs after the primary and the secondary oil production. So as shown in this figure, in a WAG, the gas is injected followed by the water, and one gas cycle, or one WAG cycle equals the water cycle followed by a gas cycle. So the problem now encountered by the SWP project is that as a CCUS project, the SWP is required to achieve different objectives during its development. So specifically in this work, we are considering 2 different objectives. The first one is that it needs to have a considerable amount of CO2 production, and this is directly with the project profit. The second one is that it needs to have the required amount of CO2 storage, and this is to help to reduce the greenhouse gas emission. So our work is to come up with the ways to co-optimize these 2 objectives simultaneously and obtain the acceptable solutions for both these 2 objectives. So to do that, we use the artificial neural network to train our proxy model, and then we couple this proxy model with the multi-objective particle swarm optimization, or what is what we call the MOPSO, to find and generate the Parut front of these 2 objectives in this work. For a problem with different objectives to optimize, so a traditional way is using a Greek equation to combine different objectives together. For example, for a problem with 2 objectives, F1 and F2, to minimize, you can have a function ft to combine these 2 together, and then you apply different optimization algorithms to find the optimum solutions on ft. But in this work, we use MOPSO to generate the Parut front of these 2 objectives, which is shown in the lower figure. So as you can see, the blue line formed by those undominated solutions is called the Parut front. Compare the Parut front with the aggregate equation method, it has some advantages. The first one, it can display how F1 changed versus F2. The second one is that it can give optimal solutions for both these two objectives. The third one is that it can provide more flexibility on choosing the required objective function values. And this is what cannot be done by using the aggregate equation. So in our work, because we want to use the MLPSO to generate the part font, it will require us to have a very large amount of the computation. So this figure shows you the process of a traditional numerical simulation process. So as you can see, input parameters are given to the numerical model. And if you run the numerical simulation, it will give you some simulation results. But there will be a problem if your model is very big. So your simulation time can be very, very long. Specifically in our work, our model will cover the whole FWU field. So that means running one simulation can take a very long time. So this is what we cannot afford. So that's why we need to use a proxy model. Proxy model is the reduced order alternative of the high fidelity numerical models. It can help to save the computational overhead. If we can generate the proxy model, the computational speed can increase by orders of magnitude. So that's why in our work, we will use the multi-layer network to train the proxy model. We prepare 597 sets of the training data. For each set of training data, it has 4 input parameters: the auto cycle, gas cycle, the produced bottom hole pressure, and the auto injection rate. For the training targets, we have 50 points to represent the cumulative oil production time series and also the CO2 storage time series. And to train the proxy, firstly, we generate a pool of different architectures. When we are talking about these different architectures, specifically, we're mainly considering the number of the neurons in each hidden layer, number of the hidden layers used, and also the activation functions. We're going to determine the performance of each architecture based on this equation. And also the performance is calculated based on the blind test data. I need to point out that the blind test data are not used to train the proxy itself. This is because we would like to test whether the trained proxy can handle the input data with different parameters. If the model, if the proxy can have a good performance on this blind test data, so that means we can use the trained proxy in a wider range. So finally, the architecture with the lowest error will be used in our following work. Okay, so we found that the optimal architectures has 5 hidden layers. And also, we list the neurons used in each hidden layer. The average error for this architecture is found to be 0.54%. And about 50.5% of all the blind test data has an error less or equal than 0.5%. About 98% of all the blind test data has an error less or equal than 1%. The highest error of blind test data is found to be 2.61%. To furtherly validate this proxy model, we select 3 data sets from all the blind test data with the highest, median, and the lowest absolute relative error. So as you can see, the upper 2 plots is the worst case, which has the highest error of 2.61%. And the median one has error of 0.49%. And the best case, shown in the lower 2 plots, has the lowest error of 0.3%. So although there still exists some difference in the worst case between the simulation predictions and also the proxy results, but if you remember, about 98% of all the blind test data has an error less or equal than only 1%. So we can see those cases with relatively higher error only takes a very small part among all the blind test data. So we can see our trained proxy is a robust one, and we can use it to make predictions match very well with the simulation results. Based on the trained proxy, so finally we generated the power to front, which is shown in this figure. So as you can see, it can give us the range of all the optimal solutions of F1 and F2. Specifically, the F1 is the cumulative oil production, which is in 10 to 7 barrels. And the F2 is the CO2 storage, which is in 10 to 6 tons. We also run other 5,000 random experiments to validate this parallel front. So what we do is we give the input parameters to 5,000 experiments, and these parameters are randomly selected from their range. So the results are shown here. So you can see all these 5,000 experiments are dominated by this parallel front. Or what we can see, all the solutions of these 5,000 experiments are not better than the results we found on the parallel front. So how can we use this parallel front? To do that, we define two treated factors in this work, the alpha and 1 over alpha. The physical meaning of alpha is the increment oil production obtained when the CO2 storage is reduced 1 times 10 to 6 metric tons. And the physical meaning of 1 over alpha is the incremental CO2 storage obtained when the oil production is reduced 1 times 10 to 7 barrels. So we're calculating the values of these two factors. And based on these two values, we divide the parallel front into 4 different sections. OK, so now let's give examples how to use it. For example, if the project requires us to have more oil production in the next 20 years, OK, so we'll see, firstly, we would like to choose our objective values from the right side of this figure, because the right side has a higher oil production. And then we're going to compare the value of alpha of the section 3 and section 4. Because we found that the section 3 has a higher value of alpha, which means it will have more oil production when the CO2 storage is reduced the same amount. So that's why we'll see our recommendation will be from the section 3. On the other hand, if the project requires us to have more CO2 storage in the next 20 years, so this time, firstly, you would like to select your values from the left side, because the left side you have more CO2 storage. And then this time you compare the value of 1 over alpha. The section 1 has a higher 1 over alpha, which means you will have more CO2 storage when your oil production is reduced the same amount. So our recommendation would be from section 1. Another application of this parallel front is that if your project requires you to have 2 million tons of CO2 storage, for example, and then by investigating this parallel front, you can see the optimum solution for the cumulative oil production would be 1.53 times 10 to 7 barrels. So the parallel front is very easy and useful for the engineers to quickly know what is the optimal solutions for both these two objectives. So furtherly, we also compare the parallel front with the aggregate equation. So we make the FT2 plus F1 and F2 together and applying the PSO to find the optimum values on FT. It found that the highest value found by using PSO is 3.673. And then we're also calculating the F1 plus F2 of all the particles on the parallel front. But we found that the parallel front can even find a higher value. So to further compare these two different methods, we picked 3 cases from the parallel front. The case 165, 175, and the case 200. Specifically, the case 165 has the same value on the F1 plus F2 as the results found by using the PSO. And the other 2 cases has a higher value than the results found by using PSO. And then we go back to check how the cumulative oil production and the CO2 storage will change versus the time. And we found that all these 4 cases are totally different. Although, as you can see in these figures, although the difference between each case might not be that big, however, it can still tell us something very important. The first thing is that using a gradient equation might not give you the real optimum value, because in our case, the parallel front can find a higher value. The second thing is that even for the same value of the F1 plus F2, using a gradient equation can only give you a unique solution. But by investigating the parallel front, it can give you all the possible combinations that give you this value of F1 plus F2. So finally, we draw some conclusions from this work. So firstly, we develop a framework to optimize the CO2 storage and the oil production. The second one, we generate the parallel front, and it gives us the range of these 2 functions. The third one, we define 2 treated factors. By using these 2 factors, we're going to recommend objective value selection based on different engineering requirements. It's useful and helpful. The last but not the least, the parallel front is more robust than using only the aggregate equation because for two reasons. The first one is power front can find even better values than using aggregate equation. And second one, even for same values of the F1 plus F2, power front can give you all the possible combinations. So this is what cannot be done by using aggregate equation. And thanks for your attention, and I'm pleased to answer all the questions.
John Yu, has anybody got questions? Yes.
Thanks. I'm Amir, Northeastern University. So I have two questions, technically. So first one is, what made your model NP hard, your optimization model NP hard, that you used PSO algorithm? Otherwise, you can use exact optimization algorithm to solve it. And the second question is, how did you ensure that you didn't end up stuck in the local optima and you could find the global optima in your optimization model?
Okay, so your first question, let me just repeat. Your first question is, why will you use the proxy model but not the simulation model, right? Numerical simulation.
In the optimization model.
Yeah.
Yeah, like instead of using the exact optimization algorithm, you used PSO, right?
No, actually, the PSO is just the algorithm, the optimization algorithms. I'm guessing you're asking this, right? Why will you use the proxy model?
No, I'm asking why did you use PSO to solve for your optimization model?
Oh, for the multi-objective, right?
Yeah.
We just pick one algorithms, and this is a very high efficiency and computational.
Yeah, because these types of algorithms usually give you the close to optimal solution, not exact optimal solution. So if you can solve an optimization problem with the exact algorithm, so it's always better to do that. So sometimes when you have NP hard problem that you cannot solve it with the exact algorithm, so you usually use meta-heuristic algorithms like genetic algorithms or PSO to solve it.
My understanding is for this case, we cannot solve the real optimal solutions because this is if you say it in a mathematical way, it's a very big matrix. If you use you want to solve it, it's very difficult. So that's why we can only use some kind of optimization algorithms to find.
Yeah, so that was exactly my first question. So what made your model NP hard and hard to solve with the exact algorithms? So what factors? So what you have?
Because the model is very complex. We have a lot of input parameters. We have a lot of we have very big matrix. So if you use the any solvers you mentioned, it will be very, very complex.
Do you have a second question? Or?
Yeah, the second question was, how did you ensure that you didn't stuck in the local optima? Because when you use these meta-heuristic algorithms, you have to ensure that maybe sometimes you stuck in the local optima instead of the global optima.
Yeah, that's the problem. But when we use these algorithms, actually we do a lot of trials, and we will find, if you see this, so that's why we're going to, you see the upper figure. So one way to avoid the local minimum is that you see there is almost a stable plane when you're running more simulations. If there is no increase, that means more or less you cannot find a better solution, right? But when you use a PSO, so how we validate is that we run, that's why we run this 5,000 run experiment. If we cannot find a better solutions, so we can see, because we are we are engineers, right? This is an engineer problem. So we are okay with that if we cannot find a better solutions. So we are okay with that.
Okay.
I agree with you. In mathematics, of course, there is a possible you can find a better solutions. But in the engineer problem, the global medium maybe is very close to the local medium. So our tack is that if we cannot find better solutions, we're okay with our solutions.
We might leave that there. Thank you very much.
Thank you.
Can we thank? Yes, and thank you everyone for staying the distance. Thank you, Sarah, and thank you for the people recording up the back, all your efforts, much appreciated. And it's lunchtime, yeah.